Welcome back to this session. Last time we have discussed two important aspects of amino acids. One is isoelectric point and the other is the chirality. Chirality, we have said that is very important to maintain in order to develop drugs, and the other point is the isoelectric point, that is very important in order to separate amino acids, and not only amino acids, peptides and proteins. So, before we go on to any next topic, we start with a problem. So, suppose I have a mixture, I have a solution containing a mixture of 3 amino acids, glycine, alanine and glutamic acid. Okay? Glycine, alanine and glutamic acid. And suppose the isoelectric point, this is we are assuming, it may not be correct, we are not taking any value from the literature, but let us assume that the isoelectric point of glycine is 8, the isoelectric point of alanine is 6.5 and isoelectric point of glutamic acid is 3. Okay. So, that means Pi 3 is less than Pi 2 less than Pi 1. Now, I want to separate. So, what I need to do? What I need to do is basically first select a matrix on which I can apply the solution of the amino acid. What kind of matrix? It could be a piece of filter paper like the Whatman filter paper, or it could be a gel like substance made up of polyacrylamide or agarose. So, these are the different matrices you can use, okay. And depending on the matrix, we have different names of the process. Process means the process is that we have the matrix and on 2 corners we apply the positive and the negative electrode and apply the voltage. Okay. The process is called electrophoresis. Electrophoresis is basically the mobility or the movement of a molecule under the influence of an electric field. Okay. So, what I need to do? I need to first apply the solution containing the amino acids in the middle, okay. And the one which has got the Pi in between the other 2, that means the middle one, which is 6.5, which is for alanine. So, I maintain the pH of the medium on which this is immersed, this paper is immersed or the gel is immersed. I put it, I keep the pH of that medium as the Pi of the, which is in the middle of the 2, in between the 2, 8 and 3. Okay. So, 6.5 is the pH I maintain for the buffer system here, and then I apply the voltage. Now, what will happen? Alanine being neutral at 6.5 will not move, that will remain here, and then the other 2, what will happen to the other 2? They will remain as charged species. Now, the question is what will be their charges? Now, what happens that if the pH is less than the isoelectric point, then this species will remain as the, if the pH is less than the isoelectric point. Okay. Isoelectric point, it is neutral. So, the pH that is maintained is less than the isoelectric point. So, in this case 6.5 and the isoelectric point of glycine is 8. So, if the pH is less, then that will be present as a positively charged species, because it has not crossed the isoelectric point 8. And if the pH is greater than the isoelectric point, then the species will be present as the ionized, the anionic form. Okay. So, that is what it is. That means, the rule is that if this is the pH and this matches with the Pi, then if you maintain the pH on this side, the species will be positively charged, and if you maintain the pH on this side, the species will be negatively charged. So, that is it. So, now we have to decide glutamic acid has a Pi of 3, now which is less than the pH, which is less than the pH that is maintained. That means, it is on which side then? It is on the negative side, because the Pi is 3, but the pH is much more than that. So, it will be present as a negative form. So, this will move, the glutamic acid will move in this direction and the glycine will move in the a negative direction, because glycine's pI is still not crossed, the pH is 6.5. Until you cross the pH 8, it will not be present as a negative species. So, below 8 it will be present as a positively charged species. So, now what will happen? If you apply the voltage for a certain amount of time, now you will see here is the alanine and glycine may move somewhere here, and it all depends on the molecular weight, and the glutamic acid will be somewhere here. So, now these 3 spots are separated. Okay. So, 3 amino acids are separated. I hope the principle is clear. The principle is that if you have 3 amino acids, you take the pH for the pi which is in between the other 2. Okay. Now, you can question me that if there are 4 amino acids, what are we going to do? Okay. Now, in that case also there is another point, this mobility, the mobility of this, as I said that molecular weight is an important issue, and there are amino acids which are having side chains which can form hydrogen bonds, which can form interactions, more interactions with the gel. See, when you have applied an electric field, there is a movement of the species because of the charge, but something is also dragging it behind. And what is the dragging force? The dragging force is the interaction of the molecule, that means in this case amino acids, with the matrix. The matrix is, if it is a paper based matrix, so it will be a cellulose, it is a carbohydrate which can form hydrogen bond, which can have hydrogen bonded interactions with the amino acid side chains. So, we can easily pick out that if there is a amino acid, if it is between a choice between glycine and serine, then serine will have a lower mobility than the glycine under the influence of the same applied field. Okay. So, even if you have 4 amino acids, their mobility equivalent to which is called RF. In organic chemistry, we have RF, that means the amount of movement related to the solvent front. In this case, it is the mobility, differential mobility of the amino acids, which can allow you to separate the amino acids, but by applying this simple isoelectric point rule. Okay. For 3 you can take the middle one, but for 4 or 5 if you have more amino acids, then you have to do a longer time electrophoresis, so that they become separated one after another. Okay. So, that is the isoelectric use of isoelectric point. Now, let us one point is here, which now the basic point is that how do I know where is the amino acids in this piece of paper, because amino acids are not colored. So, although I have spotted the amino acid here to start with, and they have separated into 3 spots, but the question is how do I know where are these spots? Okay. So, that means I should have something to visualize these amino acids. Okay. Now, amino acids unfortunately, they do not have fluorescence, that if you shine light that it will fluoresce. So, that is that you cannot do, but there are other chemical tests for which can give color for the amino acid, and that will show the location of the amino acid at a certain place. So, what is that reaction? The reaction is called, it is a well known, you might be knowing it already, Ninhydrin test. Okay. Ninhydrin, maybe E is not there, sorry. Ninhydrin test. This Ninhydrin test is what? That it is a reagent in which if you add an amino acid and then you heat it, you get a bluish violet color. You get a bluish violet color for all amino acids except proline. I will show you why proline does not give positive Ninhydrin test. It gives some color, but which is different from other amino acids, but all the other amino acids give a bluish violet color with the ninhydrin test. Okay. So, now what you do, suppose my question is, after the electrophoresis I have bands here. Okay. These are the spots of the 3 amino acids. How to know where are they? So, what I do, I spray this ninhydrin reagent, it is just ninhydrin in acetone solution. I spray it and then I heat the paper with a hot air gun, and what I will see? I will see nothing but that these spots will be somewhere bluish. See, it is a mixture of something like this bluish violet. I think you cannot make this color here. It is a, because it is a single color, it shows slightly violet color will be there, something like this. Okay. So, this is the way you can visualize the amino acid. Now, there are 2 questions that come from this. First of all, if you treat this with ninhydrin, your amino acid is lost. You are not basically, you separated them, but all the amino acids have reacted with ninhydrin and you cannot recover the amino acids. That is number 1. And number 2 is that why, the basic question, that why does amino acid give color with ninhydrin. Okay. Third is, what is basically ninhydrin, what type of reagent it is, what is the structure. Okay. Now, let us first answer one by one. First is, the question is, if I react all the spots with ninhydrin, then the amino acid is lost. I can only, this will only demonstrate the mixture has 3 amino acids, that much I can tell. Okay. But I am not getting, I cannot recover the amino acids from this. Okay. So, to bypass that, what usually is done is that you take the same piece of paper, but instead of giving a spot, now what you do, you give a, you apply the solution as a band like this, okay, and then do the electrophoresis. So, now what will happen? Alanine will remain here. I am taking the same example like earlier, and there will be glycine somewhere here and aspartic acid depending on the mobility, as I said. I think one more thing I should say, the mobility not only depends on the molecular weight, but it also depends how far away you are from the isoelectric point. That is also important. How far away is your pH from the isoelectric point. Okay. So, they will move at different, this is your starting point, this is the alanine, this is glycine, and this is your aspartic acid. Okay. Remember, if you take the single letter symbol, glycine is G, alanine is A, aspartic acid is D, aspartic acid. Okay. That is the, you try to pronounce it at aspartic acid. So, D. So, DAG. Now, what you do, in order to isolate back the amino acids, the best way to do is you cut a strip, a small strip from this end, and you cut a small strip from this end. Okay. So, now I have 2 strips here from these 2 ends. Okay. And then I spray ninhydrin on both, and then again heat with a air gun. So, what I will see? I will see a band here, maybe I will take this, I will see a band here, I will see a band here, I will see a band here, and the same thing I will see here, see there and see there. Now, what you do? You put those things again back to the, from where you have taken them. So, now I will see a band here, a band there, a band there, and a pink, and this, actually this is a kind of bluish violet, or the color is it is a kind of means there is no well defined color that I cannot say that this is pink or this is magenta. So, but some books say that it is bluish violet or bluish pink type color. So, this is the color. Now, what you do, once you reconstruct it, now take a piece of scissor and what you do, you take back, cut this piece of paper from here, cut this piece of paper from here, taking the width of here, what is the width of your band, and then cut this piece of paper. Just to make sure that you are taking all the amino acids, you take a extra over there, okay, little bit extra portion you should cut. Now, it is very easy, you take this piece of paper, cut into small pieces and put it in a flask, add water. These amino acids are mostly soluble in water, and then filter, and then from the filtrate, if you evaporate the filtrate, you get the amino acid. Okay. So, this is how the separation by paper electrophoresis is done. You cannot do it if you have gel here. It is not applicable for gel, remember. It is applicable because for gel it is very difficult to cut this and then again reconstruct it. For paper this is very useful, and you can have very big size filter paper and do it. Even you can isolate milligram quantities of amino acids by doing this technique, separation by paper electrophoresis. Okay. So, you see the importance of isoelectric point, and you now, so the first question is solved, that how to detect the amino acid and how can you isolate it back. Okay. So, that is done. Next is what is the reaction, what is ninhydrin, why does it give a violet that bluish violet color. Okay. Now, ninhydrin has a structure which is like this. It is a trione, it is a benzene and a 5-membered ring with trione. Okay. However, from organic chemistry point of view, we know that if a carbonyl is flanked between two electron withdrawing groups, then what happens? This can exist in a form which is a geminal diol. So, it can exist as a geminal diol form like chloral hydrate. There are several examples like this. So, they are in equilibrium, diol as well as the this is the ninhydrin. Now, you are taking an amino acid. So, write the amino acid NH2, CO2H and R. Now, out of these 3 carbonyls, the most reactive carbonyl has to be this one, the most electrophilic carbon has to be this one, because these 2 carbonyls, this carbonyl is flanked between 2 electron withdrawing carbonyls. So, the NH2 is going to react with this carbonyl. So, if that reacts, what is the reaction between a carbonyl and an amine, primary amine? It forms the imine. Okay. First attack to the carbonyl, that goes there, takes the hydrogen, and then the next step is the nitrogen lone pair again flies back and you form what is called an imine. I am just skipping that step. Okay. N, then that alpha carbon, then CO2H, C double bond O, OH, and this is your R. Okay. However, this is not very stable. Very not stable means this is a very basic concept from organic chemistry, that if you have a carboxy group COOH, then a carbon and then an electron withdrawing group like a carbonyl, then what happens? It loses carbon dioxide very easily. That is called the decarboxylation of beta keto acid. So, beta keto acids are very unstable. They lose carbon dioxide. That is why when we buy ethyl acid, acetoacetic acid, we had to buy it as the ester form. This is CO2ET, in order to block the release of the carbon dioxide. Now, if you look at this structure, it is very similar. This is carboxy, then a carbon, here there is a carbon, then nitrogen, then a double bond, then another electron withdrawing group. So, this is even more facile. The structure is such that it will facilitate the release of carbon dioxide like the arrow that I am showing. So, it loses carbon dioxide, and as it loses carbon dioxide, what is being formed is this O minus, and then you have this is N. So, there is a this is a very good way of decarboxylating amino acids, decarboxylating amino acids. Okay? Because decarboxylation is not very easy. Usually, you need lot of energy to decarboxylate a carboxylic acid, but here ninhydrin is acting as an electron sink. See what is happening? What is an electron sink? When electrons is going towards the direction, that direction means there is must be some, it is like a black hole that it is trying to absorb whatever is coming out. Here it is electrons. Electrons is going to the to this direction, that means this is electron sink. So, what is being formed is an imine like this. Okay. I think something is missing, a double bond is here. Okay. Then there is a hydrolysis of this imine. If there is hydrolysis, then what will happen? Then this will form, imines are not very stable unless they are aromatic, you must be knowing that. So, you have this C double bond O, this is O minus, and then that will become NH2, and you have generated an aldehyde. What is the aldehyde R? The aldehyde R, remember, that is the R of the amino acid, but now that has no function. Now, what will happen? This amine that what is generated, it reacts with another molecule of ninhydrin, because this amine is now a new nucleophile that is formed. So, this new nucleophile will react with ninhydrin, and that will form, again this amine is going to attack this carbon followed by expulsion of water. So, that will be lost, and this will form double bond N, that means when water is gone, and then double bond N, and then you have the other ninhydrin system. Okay. This is the other ninhydrin system. Now, this is you had O minus here, you have a double bond, you have this double bond. So, this is the product, that is the colored compound. Why it is colored? Because you see the extensive conjugation here, this comes here, that goes there, that can go there, that can come there, or it can go there, that can go there. So, it is an extensively conjugated system. So, that is why you see the color, and why you see the same color for all amino acids, because ultimately the color is not due to the R group. The color is basically the between the two ninhydrin molecules, which is in between there is a nitrogen. This nitrogen actually is the nitrogen from the alpha amino acid. So, that is why all amino acids give the same color, except, again I repeat, except the Prolene. Now, what happens to Prolene? Now, let us see what happens during the ninhydrin reaction of Prolene. Now, Prolene being a secondary amine, so we expect some difference, and that is the only secondary amine, and indeed it gives a brownish yellow color with ninhydrin. Now, why is that? Because the reaction stops at an intermediate step. So, I will write the reaction and the along with the mechanism. So, the ninhydrin is here this structure, okay, tricarbonyl compounds, and we know that it also exists as the in equilibrium with the geminal dihydroxy, because it is flanked between the two carbonyls. Okay. Now, Prolene has a structure which is represented by this, and to the correct stereochemistry is CO2H, of course, but this reaction does not depend on the stereochemistry, it gives the same color irrespective of whether you use L amino acid or D amino acid, that is an important point. But here we are showing the D amino acid, the L amino acid, this is 1, that is 2 and that is 3, hydrogen being alpha. So, this is S. Now, the first reaction is the same like the earlier cases where primary amine is used. So, that becomes OH and the nitrogen loses the hydrogen. So, then you have an intermediate which is like this, a carbonyl, and then you have OH, you have this carbonyl, and that is linked to the Prolene nucleus. Now, what will happen? This nitrogen will utilize its lone pair and remove the OH as water. It takes up hydrogen from water. Okay. And in the process, unlike in the previous cases, here the nitrogen remains as a positively charged species. Sorry, just a second. The nitrogen remains as the positively charged species. So, you have a double bond here, the nitrogen, and it is an iminium ion now, OH, and this is plus. But still there is electron withdrawing to carbonyl groups, and this is present at the beta position. So, this double bond is under tremendous stress, being linked to a positively charged nitrogen and also to electron withdrawing carbonyl groups. So, there is now scope for decarboxylation like the previous cases, and you have this relay process of electron shift, and that gives you the decarboxylation of Prolene. So, now the Prolene has just become a pyrrolidine, a 5-membered heterocyclic nitrogen is what is called a pyrrolidine. So, it becomes a pyrrolidine, and you have an intermediate like this, O minus, and this is in, and that is the pyrrolidine. So, you see the stereochemistry does not matter, because all these Ninhydrin reactions are associated with liberation of carbon dioxide, destroying the stereochemistry of the stereogenic center. Okay. So, now this is, there is a double bond here, and this is the one. So, that becomes a pyrrolidinium ion, and this is what is the yellow, the brownish yellow I was talking about, because this has got a resonance structure like this. So, because of this resonance, so you get a color, okay, because extended conjugation is the main cause of giving coloration, and this is the hydrogen, but the nitrogen remains the positively charged. Okay. And this is the brownish yellow color. So, Prolene behaves little bit differently, because it is not able to produce the NH2 attached to the Ninhydrin. Earlier primary amine replaces the carbonyl with NH2 and that reacts with another Ninhydrin, but in this case only one Ninhydrin is associated with the pyrrolidinium in the form of pyrrolidinium ion, and this pyrrolidinium ion is coming from the decarboxylation of the Prolene ring. So, this is brownish yellow. So, that is the situation with Ninhydrin reaction. Remember, all amino acids except Prolene gives a deep violet, blue violet color, and that is same, the color is same for all amino acids except Prolene, because all amino acids it is not the R group, the R group is not there, because there is decarboxylation and also liberation of the destruction of the, along with you release the R, and so it is the amine ultimately that forms the color. It reacts with another Ninhydrin. So, the color is independent of the nature of the side chain. In case of Prolene, we have a slight difference, because it cannot liberate the primary amine, and so it stays at this in these two resonating forms. So, that becomes the brownish yellow. So, that ends up the detection issues of amino acids, and next is our, we will go to the synthesis of peptides, how these building blocks are added one after another. We know that amino acids combine AA1 and AA2. So, that means 2 amino acids are combining and that gives what is known as a peptide. Okay. Let us give some examples. Suppose glycine and say alanine, okay, NH2 CO2H and there is a CH3. Now, they react with each other and form what is called a new bond is formed, that is between the carboxy of the glycine and the NH2 amine of the alanine, and you get what is called a dipeptide. Okay. Now, the point to note is here that this is a very facile reaction, it should be, because there is elimination of water, a stable molecule of water that is being eliminated. Okay. So, that means its delta G is highly negative. So, it should be a spontaneous process. However, it is not a spontaneous reaction. The thermodynamics says that this reaction should go, but as you know that delta G negative does not immediately say that the reaction will take place under ordinary conditions. To have this reaction taking place in a test tube, you have to provide what is called activation energy. We have to do something so that the activation energy is lowered and the reaction takes place. So, that is number one, that this bond is very stable and this reaction is very thermodynamically favored because of the loss of water. However, the reaction does not take place if you mix an amine and an acid, because there is a high activation barrier. Okay. The other point to note is that this is alanine and this is glycine. They can react in two ways. One, that they can form a peptide which is GA. Now, we should start writing the symbol GA, glycyl alanine, or it could be that alanine, the alanine carboxy reacting with the glycine amine, that could be the other way around. Okay. Then you get what is called alanyl glycine. This is glycyl alanine, this is alanyl glycine. So, 2 amino acids can react to make 2 different peptides, they are not same. In this case, there is this amine functionality which is free and the carboxy which is free at this end, and in this case the glycine carboxy is free and the amine is free on this side. Okay. Now, when you write a peptide, then the traditional way of writing is that on the left side amino acid, the amine is the free, and on the right side, the extreme right side, the carboxy is free. That means, if I have an amino acid, suppose X, Y, Z, P, Q, whatever, just an arbitrary. If I write this, suppose these are all amino acids, then immediately it says that this R has carboxy free and this has got NH2 free, and this will be called N terminus amino acid and the other will be called terminus amino acid, and this is the C terminus amino acid, C terminus or the carboxy terminus. Okay. And the other important point is that, although this is very simple, but the other important point is that a dipeptide has a notion, sometimes the students get confused. Dipeptide means there should be 2 peptide bonds, tripeptide there should be 3 peptide bonds, that is not the case. The name is such, dipeptide means a peptide containing 2 amino acids, it is not the number of peptide bonds. The number of peptide bonds is always less than 1 than the number of amino acids that are reacting. Of course, there is one intricate point here, that is, we are only talking about linear peptides. we are not talking about any cyclic systems, because the whole scenario will change if I start making cyclic peptides, which are also possible. We are only talking about linear peptides. So, if there are linear peptides, then what happens? The number of peptide bonds will be one less than the number of amino acids that are reacting. Okay. So, now there are two things which are very important. One is how to synthesize peptides. How do I do this reaction? I say this is thermodynamically favored, but this is kinetically disfavored. This has got very high activation barrier. So, one is that the synthesis, but this is we are talking about chemical synthesis, we are not talking about biosynthesis, because if you think of the biosynthesis, that means how proteins are made in the body, at that time activation comes from somewhere else, because in the body you cannot provide high energy, high temperature, high thermal condition, that is not possible. Okay. So, synthesis is one, which is chemical synthesis. The other point is that if I have a peptide, then how do I know the sequence of the different amino acids? So, these are the two challenges that first the protein chemist faced, that how to know the sequence of amino acids. By the way, that is what is called the primary structure of proteins, and the other is how to make, how to synthesize amino acids as per a design. Okay. So, next lecture will tell about that.